Hi folks, in this video we're going to solve a few problems in simple harmonic motion. All these problems involve situations where we have to first identify if it is simple harmonic motion, and if it is, what is the frequency. So let's get started with the first problem. A wire or a string under extremely high tension with a bead attached to the center of it. So this wire or string is under a high tension T, and the bead, which is right at the center, has a mass m. The length is L and the bead is right at the center, so on each side we have L by 2, and we pluck it in the vertical direction and release it, so it's oscillating in the vertical direction. At any instant of time while it is oscillating, it might look like this. Now naturally, when the string is stretched like this, the tension in the string will become different, but the original tension T is assumed to be so large that the change in the tension is negligible, and we can continue to assume the tension in the string is T. In that case, the forces on the bead from the two sides are T and T as shown. Now the horizontal components of the two forces cancel, leaving only the vertical components. So the vertical components add and result in a net force which points back towards equilibrium, so it's a restoring force. So naturally, it'll accelerate towards the equilibrium position, and by the time it reaches that position, it would have acquired enough velocity to overshoot, and it'll oscillate back and forth. Let's say that at this instant of time, the angle here is theta. Then, the component of the tension pointing back towards equilibrium is T cos of 90 minus theta, so T sine theta, and this tension on the left will produce an equal component, so the net restoring force is 2T sine theta. Now if you look at this drawing, let's say the displacement at this instant of time is x. Notice that I've taken x as being positive upwards, and since this force points downwards, we should put a minus sign out there. And then we equate this, the net force, to the mass of the bead times its acceleration, d2x by dt squared. Now we are going to make an assumption that theta is very small. If theta is very small, remember theta is in radians, so sine theta is approximately equal to theta, and it's approximately equal to tan theta. So we are going to equate it to tan theta, so minus 2t, sine theta is replaced by tan theta, which is x by L by 2, L by 2. And that is equal to m d2x by dt squared. And you can see, comparing it to the mass in spring, remember our mass in spring? Spring constant K, mass m. So if you remember the equation for this one, the force was minus kx when the displacement was x, is equal to mass times acceleration. And this differential equation is identical to the differential equation that we have, except what plays the role of k is 4t by L, and the role of m is played by m. Now the solution for this was an oscillation with a frequency of 1 over 2 pi root k by m. So we can write down the solution for this, which gives us a frequency of 1 over 2 pi root of what plays the role of k? 2 times 2, 4t by L. So 4t by L, and there is an m at the denominator, ml. So this is the frequency. So now you can see our strategy. Our strategy in every problem is to disturb the object from equilibrium, find the restoring force or the restoring torque. If it is a restoring force, write down force is equal to mass times acceleration. If it's a restoring torque, write down torque is equal to I alpha, and compare it with the spring and mass equation and simply write down the frequency. Let's try it out with a rotatory problem. We have a simple pendulum of length L and mass m. Now a simple pendulum is one where the string is effectively massless, that is negligible mass, and the bob is so small that it can be treated as a point mass. Now this is oscillating, and at some instant of time, let the angle be theta. So theta, of course, is a function of time, and we can ask ourselves, at the instant that the angle is theta, what is the net torque acting on it. To find the net torque, we need to know what are the forces acting on the system. What is our system? The bob plus the string. So on the system, at the top, there is a force in some direction which we do not know, which is the force exerted by the support on the pendulum. So I'll draw it in some random direction and call it F. And of course, we have good old mg acting downwards. Now if I take the torques about the pivot, which is O, the torque of F is 0 because it passes through that. And how do I find the torque of mg? That's very simple. We follow this procedure where we take the line of action of the force and multiply the force by the perpendicular distance to the line of action. The perpendicular distance, we'll call it R perpendicular, is equal to L times sine of theta. This is also theta. So L sine theta. So the torque is mgL sine theta. Now we got to be careful here. Look at theta. Theta equal to 0 is vertical. Theta equal to 45 will be right in the center. Theta equal to 90 is horizontal. So the moment we call this angle theta, you can see that it increases in the anticlockwise direction. So we have chosen anticlockwise as positive. This torque due to mg on the other hand is clockwise. So I should put a minus sign. That is equal to the moment of inertia of the pendulum. The string is massless. So we only have the moment of inertia of m, which is ml squared about an axis through O. And this is I times alpha d2 theta by dt squared. Once again, we compare this with our spring and mass. Minus kx is equal to m d2x by dt squared. As you can see, x theta plays the role of x. ml squared plays the role of m. But hold on for a second. I do not have theta here, constant times theta, but I have sine theta. So the simple pendulum does not execute simple harmonic motion. However, for small theta, sine theta is to an excellent approximation theta, as long as you are measuring theta in radians. In that case, the equation becomes minus mgl theta is equal to ml squared d2 theta by dt squared. And now this is identical to the spring and mass equation. So we can immediately write down the frequency 1 over 2 pi square root of k by m. What plays the role of k? M cancels here. GL divided by L squared. So the frequency is 1 over 2 pi root g by L, and therefore the time period is 2 pi root L by g. A very familiar result. Let's go on to the next problem. This next problem is extremely interesting. It's a cubical block of wood of volume 8 cubic meters. It's a big cube. That means it's 2 times 2 times 2, 2 meter by 2 meter by 2 meter cube. And let's say its relative density is 0.6. That means the density of wood of which this block is made divided by the density of water is 0.6. Now it floats in water. And we push it down by a small amount and release it so it bobs up and down. Question is that simple harmonic motion? And if so, what is the frequency? This is a problem in Archimedes' principle. So I should remind you right away that Archimedes' principle tells us that the buoyancy force is equal to the weight of the water displaced. So let's first talk about the equilibrium situation. At equilibrium, there are two forces acting on this block. One is its weight and the other one is the buoyancy force. And when it is floating, that means it's in equilibrium, the buoyancy force, which I'm going to call B0, is exactly equal to weight. Now we also know, by the way, since the relative density is 0.6, 60% of this block is submerged and 40% is above the liquid surface, but we don't need that for this particular problem. I'm just reminding you of some interesting things. Alright, so it's oscillating up and down. So at some instant of time, let us say its displacement is x meters downward. We don't push it down so much that it gets fully submerged. We always keep it partially submerged. So at some instant of time, the block looks like this. It has come down by an amount x. So this is x. Notice I have taken x positive downwards. Now first I'm going to say this in words. Initially the net force was 0. So any change in the force is the new net force. Now weight will not change while it's oscillating. The buoyancy will change. So the change in the buoyancy is the new net force. So let me write that down. The change in the buoyancy, which is equal to increase in the volume of the liquid displaced, that is the extra amount submerged, times the cross-section area, which is 4 square meters. Remember, this is 2 times 2 times 2 because it's a cube. So the cross-section area is 4 square meters. So x times 4 square meters is the extra volume of the liquid displaced times density of water times g is the increase in the buoyancy. And this is equal to the net force. So let me state it differently. I'll repeat this last part. While it's oscillating, the buoyancy is changing because the amount of liquid displaced is changing. So at some instant of time, when the displacement is x, what is the net force? Since I've taken down as positive, W minus the buoyancy is B0 plus change in the buoyancy. Now W minus B0 is 0. So this gives me minus delta B is the net force. That is equal to minus x times 4 times density of water times G. Hey, what about the minus sign here? I don't see a minus sign here. Since I've taken x positive downwards, I should put the net force is equal to minus delta B. This is equal to mass times acceleration. The mass is the total volume times the density of wood. That's the mass times acceleration d2x by dt squared. Let's compare this again with simple harmonic motion. Minus kx is equal to m d2x by dt squared. The equations are identical. Instead of k, we have 4 times density of water times g. And instead of m, we have 8 times density of wood. So the frequency of oscillation is going to be 1 over 2 pi square root of k by m. What is playing the role of k? 4. Let's take g as 10. So that is 40 times density of water divided by 8 times density of wood. But check it out. Relative density is 0.6. What is relative density? Density of the wood divided by density of water. So I can plug that in here, and this becomes 1 over 2 pi square root of 8 goes into 40 5 times, 5 divided by 0.6. So many hertz. That's the frequency of oscillation of the block. Well folks, I'm going to stop this video here. We'll go on to the next video and solve a different set of problems. Bye.